Hello and welcome back to the channel where we are reviewing the Salvadori's textbook Structure in Architecture. This video is about chapter 7 and the whole chapter is about the beams. So this is quite a large chapter, so please be ready to discuss a few different types of beams such as cantilevered, simply supported beams, fixed beams, and continuous beams, as well as the secondary bending stresses. So we know that most loads in building structures are vertical, and the majority of usable surfaces must be horizontal. Furthermore, sloping members will tend to interfere with the interior's clear space, which is typically undesirable. So the structural requirements of cables are at odds with proper functioning for the floors of most buildings. And so another structural element more appropriate to the task is required. And the one that can transfer vertical loads across a horizontal distance within an essentially flat plane. So, and those are beams, they are such elements. And let's take a look at all the details. We are going to start with the cantilevered beams. You definitely are encouraged to um, try a few simple experiments and see how that works with different materials. You can see, some basic observations and see how that works and like how for example, if the length is increased, how that actually influences the cantilever deflection. So just try to play with different elements and with different lengths, and you will see the deflection, because that's important to understand the inverse proportions to the horizontal side and the load. So the effect of beam shape on bending is actually a great deal. And that's another geometrical factor that influences the magnitude of the beam deflection. So this is an influence unique to bending that does not apply to funicular tension elements, namely the shape of the beam's cross section. So in the case of a true funicular tension element, the cross section is uniformly stressed in tension. For a given cross-sectional area, whether it's round, square, or even an irregular shape, has no real bearing on the level of stress. So in bending, however, the shape of a cross-section has a significant influence on the capacity of a member, and simultaneous compression and tension stresses exist in different portions of the member's depth. So here you can see different modulus of elasticity for steel and aluminum, and also the influence of material on cantilever deflection, as well as the influence of load location on cantilever deflection. Definitely take a look at the images and you can see how pure tensile stress works under a load. So in this case, fiber may be actual plant fiber or animal hair, like we discussed in the previous chapters, or be a metaphor when completely homogeneous or non-fibrous material is used. For example, that is steel. So the deflection of the loaded tip of the cantilever is due to the deformation of the original straight beam into a slightly curved element. Such deformation requires the elongation of the upper fibers and the shortening of the lower fibers of the beam, and produces the state of stress defined as simple bending. With the elastic range of a given material, the bending stresses in a cantilever beam vary linearly from a maximum tensile value at the top fibers to a maximum compressive value at the bottom fibers and vanish at the middle fibers. So the so-called neutral surface of the beam, that's the middle. The neutral surface intersects the beam's cross-section at a line referred to as the neutral axis, which is positioned on the cross-sectional shape at its balance point, known as the centroid. Again, look at the images here. It's best to see that those are beautiful pictures and diagrams. For example, this is the simple bending of a cantilever beam, how that works, how actually it resists, and where the neutral axis goes. So please definitely take a look and make yourself familiar with that. From the standpoint of use of material, a beam of rectangular cross section is very inefficient in bending, since most of its fibers are not fully stressed to the allowable stress. Usually only the top and bottom fibers at one point along the span reach maximum values, while all other fibers are unavoidably under stressed. And you can see there are pictures just illustrating that. There are a few different shapes. For example, the cross section of an I-beam or S section or wide flange or W section as the most commonly used, rolled steel sections. So with most of the material in flanges connected by a thin web, um, and you can see pictures here. You can see the difference and you can see how that is connected and where the neutral axis actually goes. So when we split the web of an I-beam into two and shift the material laterally, that produces another cross section just as efficient in bending, but far more efficient in torsion, the box section. Box sections may be constructed of multiple separate plates in a built-up section from face-to-face channel sections welded together or made from a single long plate folded into a square or rectangular shape and welded close along its length. They're also known as hollow structural sections or HSS. Built-up sections are normally custom designed for a specific use, whereas a wide variety of standard off-the-shelf shapes of prefabricated tubular sections are available. Again, take a look at the graphics. You can see the variation of strength with cross-sectional shape. So different shape reacts differently under the load. A few box sections, how that is different. The built-up box section from face-to-face channels, from tubular steel section. All right, so the symmetrical I section and the box section are typical forms when constructed of materials with equal strength in tension and compression. Different shapes or asymmetric shapes become more logical when these strengths differ. For example, the compressive strength of concrete is approximately 1/10 of the tensile strength of structural steel. Hence, in a reinforced concrete beam, the area of the horizontal compression flange is made of concrete, and the narrow area of steel is concentrated in the web. In case of cantilevered beams, the T-beam is necessarily inverted. The flange is at the bottom and the web is at the top of the beam. So since the compressed fibers are at the bottom of the beam. And the reinforced concrete T-beam acts very much like an I-beam in which the area of one of the flanges is shrunken because its material is stronger, but T-beams of steel obtained by connecting two L-shaped sections or cutting an I section in two are also used mainly to facilitate connections with other beams. So again, refer back to all the beautiful images here. You can see the steel T-section connection. You can see the reinforced concrete T-section. And here also other images. So let's actually clarify the meaning of moment of inertia. So you know how that works. Like, for example, if you watch an ice skater perform a grand finale by starting in a slow spin with arms extended and then rapidly increasing the spin rate, and the arms are pulled inward. So that is just trying this is like the distribution of material nearer to the center, and that creates a lower moment of inertia. So the less resistance to rotation, and actually moving material away from the center increases the moment of inertia and increases the resistance to rotation. So that's kind of like similar to the materials. And moment of inertia is a property of geometry in the same way that area is a property, that area is a property of geometry. So the moment of inertia is proportional to the area of the cross section, and also to the square of a property called its radius of gyration. If it were possible to lump all the material of the cross section into one location above and below the neutral axis, and still maintain the same resistance to bending as the actual beam section, the radius of gyration is the theoretical distance to these points. And in order to understand that, please take a look at the cross section, how neutral axis is actually where that is located, and where the radius of gyration and moment of inertia, like how that is represented graphically. So definitely take a look at those, and you can see the concentrated load at free end and uniformly distributed load along the span. So how that actually reacts. Um, Again, you can see the tapered cantilever beam. You can see the here the sloping bottom of the tapered cantilever beams. So that is the visual evidence of the increased lever arm of the flange forces necessary to counterbalance the increasing lever arm of the loads. And we are moving to the lateral torsional buckling. So what to understand that concept, what that means, it is most economical to select an I-beam with flanges as far apart as possible, thereby reducing the flange cross-sectional area to a minimum by increasing the internal moment arm and decreasing the force due to bending. The compressive flange buckles by bending out in its own horizontal plane, since the web prevents the otherwise easier buckling in a vertical plane. When the web buckles, its compressed fibers bend out of the vertical plane the compression zone being located below the neutral axis for a cantilever with gravity loading. So in either case, the cross section of the beam rotates and the beam twists. So you can see there are lateral torsional buckling. So when we talk about shear, the bending effects of a load applied at the free end of a cantilever, um, that we see that, but this load also tends to shear the beam, for example, at the point where it's secured to the supporting wall. The tendency to shear occurs across the entire length in a cantilever beam. It's also independent of the beam length for a concentrated load at the end. If the beam were shorter with the same load, the load would have the same tendency to shear it. When the load is evenly distributed on the cantilever instead of being concentrated at its tip, the amount of load on the beam and the tendency to shear increases from the tip to the support of the beam. And please take a look at the shear strain and shear distribution along a cantilever beam with a concentrated load and with the uniform load. So definitely take a look at that. Also, we can see an example of a vertical shear in a row of books. So when you squeeze the books together, you create the friction between the individual books to prevent them from falling. So if there's like a pile of books, they won't fall. And the heavier the books are, the more force is required to generate adequate friction between them. So, and that's, we need to, this example to understand the vertical shear that is always accompanied by horizontal shear. The influence of horizontal shear on the rigidity of a rectangular beam may be visualized by considering the beam sliced horizontally into a number of rectangular beams of limited depth. So like those books in the example. Also, there is another example of superimposed shallow beams. A solid beam section acts as a solid single unit, whereas a beam of the same depth but consisting of multiple unattached layers will simply act as separate beams that slide past one another in horizontal shear. The magnitude of deflections for a stacking of four beams, each a quarter the thickness of an equivalent solid beam, will be 16 times larger than the solid section. So there are a few equations here. Also, the monolithic beam is 16 times more rigid than the beam comprised of four separate slices. So that's important to remember. And the essential function of the web in the I section is to develop the shear stresses necessary to have the two flanges work together. Without the web, each flange of an ideal I-beam would act as a separate shallow beam, and the moment of inertia of the cross section would be small. The flanges connected by the web act monolithically so that the I section acquires a large moment of inertia. And that is seen that the transmission of shear through the web from flange to flange is essential to the bending action of the flanges, and that shear and bending are interdependent beam actions. Please remember that this is important. So, and we are moving to the next section, that is simply supported beams. Let's take a look at that. So An understanding of the behavior of cantilevered beams provided us with the background to understand the most commonly used beam type, and that is the simply supported beam. What actually the term simply supported means? So that means that both ends are supported and the ends are connected in such a manner that each is free to rotate and the beam is free to expand or contract longitudinally. Here is another example here. You can see the concentrated load, and you can see the simply supported beam. So you can see the visual representation here. For a concentrated load applied at the midspan of a simply supported beam, it's evident that one half of this load is carried by one support and one half by the other. As with the cantilever, the load causes it to bend and deflect, but because of symmetry, the midspan section moves straight downward and remains vertical. The behavior of the simple beam can be visualized effectively as two upside-down cantilevers with their moment-resistant supports at the middle of the beam attached to one another. Then you can see the representation of the relationship between stress and deflection of simple span versus cantilever beams. Please remember there is the difference. A simply supported beam is substantially stronger and stiffer than a cantilever of the same length. For the same cross-sectional dimensions, it can carry at midspan a load 4 times as large and will deflect only 1/4 as much under this larger load than the end-loaded cantilever. So let's take a look at the effects of loading. The distribution of load is another important consideration in beam behavior. If the same total load is evenly distributed over the length of a beam, the stresses in the beam become 1/2 and the deflections 5/8, as large as when the load is concentrated at midspan. So in a uniformly loaded beam, the bending stresses are also maximum at midspan. The shearing action is maximum in the neighborhood of the supports, where the support reactions tend to move the beam up, while the total loads tend to move it down. The shear vanishes at midspan, where there is no tendency for adjoining sections to slide either up or down with respect to one another. The vanishing of the shearing action at the point where bending stresses are greater is the characteristics of beam behavior for any and all beam other than cantilevers. Unsymmetrical loads, what do? They produce similar bending and shearing actions in a simply supported beam. Concentrated loads near the supports have a reduced bending influence owing to the reduction of their lever arms, but an increased shearing effect. So the load approaches one of the support, a larger fraction of the load is transferred to this support, while the other is gradually unloaded. And please take a look at all the beautiful images here. You can see the reactions due to asymmetric loading, and you can see beam and shear. So, and we are moving further. Let's take a look at the reinforced concrete simply supported beam, how that reacts. You can see that potential tension shear cracks at the end of a concrete beam are at 45 degrees. So the ideal position for steel reinforcement to carry the tension forces is perpendicular to that direction. Please remember that when planning the reinforcement. Also, you can see the web crippling of steel beam under high shear force, and shear failure in a steel member with a thin web results from the resultant compression forces acting at 45 degrees. Please remember that. Also, built-up girders or plate girders are beams with variable flange areas built of plates and used to carry heavy loads over spans of 50 or more feet. To simplify fabrication, we discussed that that is, for the most part, is prefabricated. It is common to increase the flange area rather than making the beam depth higher near the center of the span, even though the latter technique is more effective in strengthening the beam. In contrast to downward loaded cantilevers, simply supported beams under downward loads develop tension in the bottom fibers and compression in the top fibers. The reinforcing bars in a simply supported concrete beam therefore run along its bottom and, if necessary, are increased in number or in area toward the center of the beam. Also, you can see the twist producing loads, how that works. So eccentrically applied loads will cause this phenomenon at much lower force value. Um, so the another I-beam with openings, and also you can see the castellated beam, how that works, how it's welded together, and how that is created is by cutting the web of a flanged beam in the pattern and then reattaching the top cut to the bottom with an offset equal to half of the linear cut distance. And this is how the castellated beam is created. The spaces created allow room for pipes, electrical conduit, and small ducts to pass through as well. And there are different patterns that I used. So that is just what is represented here is just one of the examples. There are multiple geometrical shapes there. Beams must be designed for stiffness as much as for strength. It is customary to limit beam deflections to about 1/360th of their span in buildings and 1/800th in bridges. A plate girder bridge 200 feet long should not deflect more than 3 inches on the maximum loads, while a beam 30 feet long is unacceptable if it deflects more than 1.2 inches. When the dead load represents the largest share of loads, beams may be built with a camber. That is an upward deflection equal to the downward deflection due to the dead load. The life load alone then induces smaller deflections, easily contained within acceptable limits. Again, beautiful images. You can see the maximum efficiency truss, how that is created and what actually needs to happen towards the center of the span. So more material in the web verticals and diagonals. At the end of the span where shear is highest. Also, there is a nice image showing the bridge at Lake Maracaibo in Venezuela. This is a beautiful cantilever bridge construction. Please take a look at that. And we are moving to the fixed beams and continuous beams. So let's take a look at that. The uniformly load simply supported beam is an inefficient structure. This is because the bending stresses in it reach their allowable value only in the extreme fibers at midspan, where the beam fibers that have downward curvature all along the beam have their greatest curvature. Again, take a look at the deflected beam axis, how that works in deflection, and you can see the bend and stress here as well. Also, take a look at the bottom fiber stress and deflections in beam with cantilevered ends. There are calculations here. It does not make any sense to go over them in the video. Please take a look, and that definitely will help you to metabolize the whole process, how that is developed. So when the ratio of cantilevered length to supported span is 1 to 2, the center deflection is small but upward, and the entire beam still has a downward curvature. The largest stresses occur over the supports and are about 1/4 as large as those in the beam supported at the ends. When the ratio of cantilever to span length is approximately 1 to uh, 2.5, the section of the beam over the supports do not rotate. The stresses over the supports are about twice the stresses at midspan, but of opposite sign, and about 1/5 as large as the stresses in the same beam supported at the ends. When the ends of a beam are built into a rigid element and they are prevented from rotating, but not from moving horizontally, one relative to the other. The beam behaves similarly to the supported span of a beam with cantilevers in the ratio 1 to 2.5. And please again refer to the images here. Such a uniformly loaded fixed end beam has the largest bending stresses at the built-in ends. These stresses are twice as large as the stresses at midspan and 2/3 as large as the stresses in the same span simply supported. The deflected axis of a fixed beam changes from downward to upward curvature at 2 points called inflection points, where bending stresses vanish and the stress reversal occurs. Fixed beams of concrete must have the tensile reinforcement at the bottom near midspan and at the top near the supports. Again, refer to the images, how that is constructed, and you can see the fixed and reinforced concrete beam. This is how that needs to happen. So you can see the rebars. It's like a model exploded. You can see how the rebars are connected, and um, there are different, in this rendering, there are different types of tension reinforcement, and also how the lap bars connect to those tension reinforcement bars. So, and we are moving to the continuous beam. So under a uniformly distributed load, three simply separate supported beams will have no interaction with one another, and so their stresses and deformations are independent and always with tension on the bottom face. When connected in a continuous span, however, compression on the bottom surface develops over the supports. Under a concentrated load, once again, separate simply supported beams will behave independently, whereas the connected as one continuous span, a heavy load placed on one span will affect the others. Also, what is important here, the stresses due to continuity will move away from the loaded span. The curvature in the continuous beam is greatest under the load and is damped out by the supports. And you can see there are changes here in the graphics in that actually in the case of continuous spans that are subjected to a moving load, for example, the bridge, the effect of heavy load along a span length will vary depending on placement, always with tensile stress below the load. In a three-span condition, when positioned at the end span, the load causes a downward deflection below it and upward deflection in the center span, then changing again to downward deflection in the opposite end span, though at a greatly reduced magnitude. So we are moving to the last section here, and that is the secondary bending stresses. So compressive and tensile stresses of constant value over the entire cross section of a structural element are called direct stresses, to distinguish them from bending stresses, which vary linearly through its depth from a maximum compression to a maximum tension. Direct stresses allow a more efficient use of the lateral material than bending stresses because they develop the same stress in every fiber of the element. The hinged bars of a truss develop their maximum resistance at all points of their cross sections, since they are acted upon by similar tension or similar compression. The bending deflection is often 2 or 3,000 times larger than the compression shortening due to the same load. So a structural element is much stiffer in direct tension or compression than in bending. Unfortunately, pure compression or tension elements are not easily realizable in practice, as the example of a simple truss will clearly indicate. Here you can see a picture, so please refer to that. You can see the compressive and bending displacements here in the beam. Also, you can see the truss bracket, how that is actually how that reacts, and you can see the bottom member in compression, how that reacts, it shortens, and the top member in tension lengthens. So that is something to remember. Also, bending action and bracket, you can see that it maintains the 90-degree angle at fixed joint, and then it actually is different in the that free that free X here. Then you can see the bend and deformations of bracket hinge to the wall. So, and if the joint is at the tip is fixed, then both the top and the bottom members will experience a combination of axial plus bending forces, with bending action particularly concentrated at the top. And also you can see bending deformations of bracket fixed to the wall. How that works, you can see the bottom member will experience a force reversal or contraflexure between the support and the tip, with the corresponding change from downward curvature at the support to upward at the tip. And this actually wraps up our chapter. Thank you so much for watching chapter that was about chapter 7, and I will see you in chapter 8. Thank you.